This is part 2 of our introduction to exponential functions, and we're going to start this section, this part, by looking at another example of an exponential function, f of x equals 2 to the x. So let's plot some points, and we're going to let's first fill in our table values, and then we're going to plot some points and see if we can draw a graph. So I chose some x values here to start out with. When x is 0, f of 0 is 2 to the 0. 2 to the 0 is 1. When x is 1, f of 1 is 2 to the first power, which is 2. When f is 2, I get 2 to the second power, or 4. When f is 3, I get 2 to the third power. Now that's 2 times 2 times 2. 2 times 2 is 4 times 2 is 8. So I have the point 38 on my graph. And then I also want to evaluate a few negative values here. So let's plug in negative 1. I get 2 to the negative 1. 2 to the negative 1 is 1 over 2 to the first power, or just a half. F of negative 2 is 2 to the negative 2 power. That's 1 over 2 to the second, or 1/4. F of negative 3 is 2 to the negative third power. That's 1 over 2 to the third, or 1/8. So now I'm going to plot these points, and I have a graph grid set up already here, and the x and y axes are labeled. And so let's plot some points from my calculations. I have 0, 1, y-intercept. I have 1, 2, 2, 4, 3, 8, 3, 8. And I also have some negative x values here that we worked with, right? Negative 1, 1/2 is a point on my graph, so negative 1, 1/2 would be right here on the scale that I'm using. Negative 2, 1/4. Negative 2, 1/4, that would be halfway up that first square. Since 2 squares is 1, 1 square is a half, so I'm half of that. And then negative 3, 1/8, now it's getting hard for me to indicate these. I just know it's going to be even closer to the x-axis right there. And I can see that there's a curve that would fit these points, shaped kind of like so. And it appears that, well, I'm kind of flattening out here as I go off toward negative infinity, right? In fact, as I look at values of x that are more and more negative, when I calculate 2 to a negative power, I'm always going to get a positive number, but a very small fraction. So I'm actually going to get closer and closer and closer to that x-axis without touching it. As x gets larger, though, these y values just take off, and they're going to be becoming bigger and bigger as I move further and further to the right. So a couple observations now about this graph that we've just drawn. The domain of this function is all real numbers. I can plug in any value of x, positive, negative, 0. The range, however, what we see is that the y values that we obtain for points, whether we look at our table or the graph, are never going to be negative. Because if I plug in a positive value for x, I get a positive y. If I plug in a negative value for x, I still get a positive y. I get these fractions. There's no way for 2 to a power to come out to be negative. And there's no way for it to come out to be 0 either. It's always greater than 0 or positive. That means the graph is always above the x-axis, never on it, never below it. And I want to say something about the end behavior. It's an important aspect of what's going on here. As x approaches infinity, as we move to the right, the function values get larger and larger and larger. The function approaches infinity, or gets larger and larger. But as x approaches minus infinity, so as we go off to the left, the graph actually flattens out along the x-axis. So we would say f of x approaches 0. The y values approach 0. And another way to think of that is the x-axis is a horizontal asymptote. I'll write HA for that, to the graph. And this is our first example of a horizontal asymptote that applies to the negative portion of the graph as x approaches negative infinity. But really the horizontal asymptote has no relevance when x gets very, very large. Now there's a little bit more I want to think about before we leave this example behind. What about, so far I've just plugged in positive and negative integer values of x. Like, what if x is equal to 0.5, a fraction or a decimal? Now, I can imagine 0.5 here on the x-axis of my graph. It seems like I'm drawing a point right there. What does that even mean for this function when x is 0.5? Let's evaluate. F of 0.5 is going to be 2 to the 0.5. Now, to give meaning to this, I'm going to think of 0.5 as a fraction 1/2, and we know that the 1/2 exponent means square root. So 2 to the 0.5 is the same thing as the square root of 2, which, if you use a calculator to check, it's about 1.4. So the point 0.5, 1.4 approximately should lie on the graph. And let's just look at the graph we sketched here, 0.5. 1.5 is right here on the y-axis. So notice that even on my picture, I'm a little bit below. I would say that's the point 0.5 comma square root of 2. Okay, square root of 2 is about 1.4. Another example I want to think about here is, what if x is equal to 1.5? And what does that mean? So f of 1.5 would be 2 to the 1.5. Now how do we give meaning to that? What's that all about? Well, it helps to think of 1.5 as a fraction again. That's equal to 3/2. And we can interpret a fractional exponent as a root and a power. That's the square root of 2 to the third power, which is equal to, by the way, 2 times the square root of 2. If you want to simplify that on my calculator, I get that that's about 2.8. So we should have a point on our graph that looks like 1.5, 2.8. Let's take a look. Here's 1.5, and if I go up to the graph, I'm very close to 3. That looks like a y value pretty close to 2.8. I'm going to write 1.5 comma. Instead of writing the decimal, I'll write the exact value, either square root of 2 cubed, 2 to the 3 halves. Maybe I'm just going to write 2 to the 3 halves power there. I just wanted to do a couple of these points where x has a fractional value involved to help us see that there really are points in between the integer values that fill out this graph of f of x equals 2 to the x. Okay. And maybe I'll just leave that on the screen for a moment. I'm going to look at one more example and may go a little quicker through this sketch. Another exponential function, 10 to the x. So the form looks very similar to 2 to the x, but the base here is different. What happens if I work with a different base, like 10 to the x? Well, table of values is set up here. F of 0 would be 10 to the 0, or 1. For 10 to the x, f of 1 would be 10 to the 1, so I get a y value of 10. F of 2 is going to be 10 squared, or 100. F of 3 is going to be 10 to the 3rd, or 1,000. So very large value, y value there. And for negative values, what's going on? F of negative 1 is 10 to the negative 1, which is 1 over 10 to the 1. That's 1/10. Or as a decimal, that would be 0.1. F of negative 2 is 10 to the negative 2, which is 1 over 10 squared, 1/100th. Or as a decimal, 0.01. F of negative 3 is 10 to the negative 3, 1 over 10 cubed. It's 1/1000th, or as a decimal, 0.001. And let's go ahead and plot some points here. I'm going to write 1, 2, 3, negative 1, negative 2, negative 3. Now, how am I going to fit these? Well, I can't. I'm going to go 10, 20, 30, 40, let's say 50, 60, 70, 80, 90, 100. I'm not going to be able to plot at this scale beyond 100. I have 0, 1. So notice that on this y-axis scale, 0, 1 is going to be incredibly close to the x-axis. I have 1, 10, that point I can plot. I have 2, 100 already. 3, I'm off the charts for my scale. But I hope from these few points you can see I'm still getting this kind of curve that turns a corner in a sense and shoots up very steeply. At negative 1 now I can't. 0.1, 0.01, 0.001, I can't really show the true effect of what's going on there, other than the fact that this graph is very, very close to the horizontal axis. So here's the graph, f of x equals 10 to the x. And my point here is just that this looks very similar to the shape of the graph we saw with 2 to the x. So there's a certain common shape that all exponential functions of a certain kind have, and I'd just like to sum that up right here. So if I'm going to write the letter b is a constant. I think we use the letter b because it's the first letter of the word base, if b is a constant greater than 1, meaning b, I can write it in symbols, b is greater than 1, then the graph of f of x equals b to the x power looks like the following picture. I'm not going to label my axes with a scale here. I'm just going to draw an x-axis and a y-axis. And I'm going to repeat this shape that we've already seen a couple times. We have a graph that's very, very close to the x-axis, starts rising up, crosses the y-axis, and then kind of turns up sharply. What's interesting is both graphs that we saw cross the y-axis at 1, at y-intercept 1, and that's because b to the 0 will be 1 no matter what the base b is. Any number to the 0 power is 1. And some facts about this graph are the domain for any base b is going to be all real numbers. The range is from 0 to infinity, with 0 not included. The graph lies above the x-axis, with no points on the x-axis. The end behavior is as follows. As x approaches infinity, f of x approaches infinity. When x is positive and large, the y values get to be very, very large. And as x approaches minus infinity, f of x approaches 0. So in the reverse direction, as we go in the negative direction, the graph flattens out. Another way to express that is the x-axis is a horizontal asymptote to the graph. So this is f of x equals b to the x when b is greater than 1. And this is an important sketch, a graph that you have to memorize.